Hello friends, welcome in this video session of heat transfer subject. Today we are going to learn extended surface. My name is Mr. S.V. Kumbar, Sharad Institute of Technology College of Engineering, Hyderabad, Ichalkaranji. So these are the contents of today's video lecture. Types of fins, applications of fins of uniform cross section assumptions, governing differential equation for rectangular fins, few useful formulae for hyperbolic function. Let us start with fins. So fin is a part in mechanical engineering where it is extended beyond its limit. I would like to give one example. If you drink tea with the help of cup and saucer, in which case you will get less time? Through saucer, right? Because here surface area is maximum. So similarly, in case of fins, surface area is maximum, right? So fins are also known as extended surfaces because it is extended beyond its limit. Now there are so many types of fins, but few fins are listed here. First one is rectangular fin. Here cross sectional area is rectangular one. Straight triangular fin, so area is triangular one and these are straight. Circular fin with rectangular section, here it is a circular fin but at the end it's a rectangular section. Next pin fin, which is in cylindrical form, that is circular in cross section, and pin fin at conical end. Now remember, this is the extended part where it is connected to the surface from where heat is to be rejected. So this is the base. This is the base for all the fins and heat will be rejected from the base surface. So fins are generally used to enhance the heat transfer for a given surface. As I mentioned earlier, if you provide more surface area, then generally the rate of heat transfer increases. Therefore, fins are generally used to enhance heat transfer for a given surface. So addition of fins can increase the heat transfer from the surface by several folds. One example is fins which are provided to refrigerator. In refrigerator, you might have seen at the back side condenser is provided in the form of coil. Now if its area is extended beyond its limit, then further heat transfer increases and here area also decreases. Typical applications of fin. First one, a radiator for automobile. Generally in automobile, engine is located at the front and here in order to cool the hot temperature of water coming out of engine, radiators are provided. Radiator is one of the heat exchanger used. If you provide fins to radiator, then the there is enhancement of heat transfer from a given radiator, so water can be cooled in quick time. Second one, air cooling of cylinder heads of internal combustion engine. You might have seen internal combustion engine for scooter, motorcycle, etc. or air compressor. Now, in case of engine, its head is extended beyond its limit. So, this is the example of fin. Economizer of steam power plant. In economizer, water is preheated with the help of flue gases, right? So with the help of flue gases, water can be preheated with the help of fins which are provided to economizer. Heat exchangers of wide variety used in different industries. Now heat exchanger plays very important role. We will design heat exchanger in upcoming lectures, but here remember, heat exchanger is a device which exchanges heat between two fluid, that is hot fluid and cold fluid. Now if we extend any surface beyond its limit, then heat enhancement takes place. cooling of electric motors, transformers, etc. Again, you have seen electric motor. So some part of electric motor is extended beyond its limit in order to cool electric motor. Next, transformers. In case of transformers also, in order to cool transformers, generally we provide fin. Cooling of electronic equipment, chips, IC boards, etc. In case of electronic devices, you might have seen heat sink in your PCs or laptop. In heat sink, generally we provide fins so that it removes heat from electronic component so that its life is enhanced. So these are the typical applications. So I was talking about heat sink. These are the fins which are provided to heat sink in case of PCs, laptops. Here these are the fins. Next, typical application of internal combustion engine. This is the extended surface. This is engine cylinder. So cylinder is here also, head is also extended beyond its limit. So these are the fins. This is the refrigerator condenser, and here the vertical lines, these are nothing but fins. And next application we have studied a heat exchanger. In heat exchanger, the middle portion is nothing but, this is the typical radiator used in automobile. These are the fins which are used to enhance heat transfer from a given object. Now, fins of uniform cross section, rectangular or circular, we are going to see governing differential equation. Before that, consider a rectangular fin. Now this is the base and this is the extended surface, that is we call it as fin. Consider a fin of length L, base temperature TO, and here width W and thickness T. Now assuming only unidirectional heat transfer rate along x-axis only, let us consider an element of thickness dx. Now through this dx, let's say qx is the amount of heat entering through this dx, and qx plus dx, that is the heat rejecting from this element dx. Now we will consider only two modes of heat exchanger here. First one, conduction, and second, by convection. So assumptions made in governing differential equation for deriving governing differential equation for uniform cross section. So first, assumptions. Steady state condition with no internal heat generation. Steady state means all fluid property will remain constant with respect to time. It will not change with time. Thickness T is small as compared to length and width, that is we have already studied, it's a one dimensional conduction along x direction only. Thermal conductivity K of the fin material is constant. Isotropic, it's isotropic material means thermal conductivity remains same in all the direction. The material is homogeneous, that is of constant density. Uniform heat transfer coefficient H over the entire length of heat. No bond resistance in the joint between the fin and the base wall. Generally, these fins are joined to this wall by joining processes. So there should not be any resistance, or we have to neglect that resistance between fin surface and this wall surface. Negligible radiation means only considering conduction and convection. Fins of uniform cross section governing differential equation. Now consider an elemental section of thickness dx at a distance of x from the base as shown in figure. This is the fin. We will consider only fin element dx. T0 is the base temperature, L is the length of fin, W is width, T is thickness. Now let us write an energy balance equation for this red colored element. So energy going into the element by conduction, that is Qx. Here observe this cursor. Energy going into the element by conduction Qx is equal to energy leaving in from the element by conduction plus energy leaving from the surface by convection. So whatever energy coming to this element Qx is equal to whatever energy conducted through this element towards this tip, that is Qx plus dx plus some amount of heat is convected out of this element Q convection. This is the energy balance equation for this red colored element. So Q in is equal to Q out plus Q out. So we have already studied Fourier law of heat conduction. So Qx is equal to minus Ka dt upon dx. This is the amount of heat conducted towards element, and Qx plus dx is equal to minus Ka d of dx t plus dt upon dx of dx. And rewriting this, Qx plus dx, Ka as it is, dt upon dx minus this negative sign is taken inside. So minus Ka d2t upon dx square into dx. And the amount of heat convected from that red color element is Q convection is equal to HAS into bracket T minus TA, where T is the temperature of that red colored element and TA is ambient temperature. So considering perimeter of this, considering perimeter, because this area will not be W into T, but it's a perimeter. Heat will be convected along this length, that is considering only perimeter. We can write P into dx, that is the surface area, H as convective heat transfer coefficient, T minus TA. Now putting this plus this is equal to this plus this, we will write this equation as minus KAC dt upon dx, which was the left side of term Qx, which is equal to minus KAC dt upon dx minus KAC d2t upon dx square into dx, which was Qx plus dx, the amount of heat conducted out of the element, plus the amount of heat convected out of the element H P into dx T minus Ta. Here just solving this equation, try to solve this equation or try to take left hand side to right hand side, we will get here it's a minus, here it's a minus, it will get cancelled because it is having both sign common. So what will remain only minus K d2t upon dx square into dx plus h p dx t minus ta. Again dividing throughout this by this equation KAC, what we will get d2t upon dx square minus m square t minus ta, where m square or m is nothing but square root of HPKAC. You might be wondered here why m square is written here, because if you divide this KAC divide by this, you will get pH, that is HP upon KAC as it is. So this is the differential equation. So remember this differential equation. We will require this differential equation while deriving other few cases. d2t upon dx square minus m square t minus ta, which is equal to 0. This equation is very important equation in thermal analysis of fins, where m is square root of hp upon ka. H is convective heat transfer coefficient, P is the perimeter of fin, K is thermal conductivity of fin material, AC is cross sectional area of fin material. Now defining excess temperature, theta is equal to T minus Ta, where T is the temperature of element and Ta is the temperature of ambient. Now if you differentiate this with respect to T, we will get d theta upon dx, which is equal to dt upon dx. As ambient temperature remain constant, so its derivative with respect to x will be 0. So d to theta upon dx square is equal to d2t upon dx square. Now, since Ta is constant, substituting this equation in earlier equation, instead of d2t upon dx square, we will substitute this equation instead of d2t upon dx square, it will be d2 theta upon dx square. We will get d2 theta upon dx square minus m square theta, which is equal to 0. So this is known as governing differential equation for rectangular fin. As I said, equation 6.1 is known as the governing differential equation for the fin of uniform cross-sectional area, and 6.1 is second order linear ordinary differential equation. Its general solution will be given by two equivalent forms. This is first solution, theta x is equal to c1 exponential of minus mx plus c2 exponential of mx, where c1 c2 are constant, and theta x is equal to a hyperbolic cos mx plus b hyperbolic sin mx, where a and b are constant. Now, to calculate the set of c1 and c2 or a1 and b, we must require two boundary conditions. Now remember, first of all check how many constants are there. If two constants are there, then two boundary conditions are required. In our case, two constants are there, so we will require two boundary conditions. One of the boundary condition is that at base temperature, that is when x is equal to 0, T will be equal to base temperature T0. And regarding second boundary condition, there are several cases. We will see those several cases in the next video lecture. So this is the basics of fins, and these are the different cases. As I told you, first boundary condition will remain same in all the cases, that is when x is equal to 0, temperature T will be equal to base temperature T0, and right hand condition, that is second boundary condition, will be dependent on these four cases. For infinitely long fin, its boundary condition will be different. Fin insulated at its end, boundary condition will be different. Fin losing heat from its end by convection, again boundary conditions will be different, right? So we will see that part in the next lecture, but before that we will see few useful relations for hyperbolic function, that is hyperbolic cos beta is equal to exponential of b plus exponential of minus b divided by 2. Hyperbolic sin beta is equal to exponential of b minus exponential of minus b divided by 2. Exponential of b plus exponential of minus b is equal to 2 cos hyperbolic beta. Exponential of b minus exponential of minus b is equal to 2 hyperbolic sin beta. Exponential of b is equal to hyperbolic cos beta plus hyperbolic sin beta. So these formulae we will require while solving the numericals based on as well as the derivation. Out of 4 derivation, we will cover 2 to 3 derivation in the next video lecture. So thank you very much.